Okay, this video is going to be about how to decide which method to use when solving a system of linear equations. We learned a few methods in Math 1. We've just learned a whole bunch of other methods here in Math 2. What this video will do, we'll review all the different methods we should know, and will hopefully help you start to understand how to decide which method to use. And when you're trying to make that decision, what you want to think about is how is the system set up, okay? And what we mean by set up is, what do the equations look like? Are they in standard form? That ax plus by equal to c, are they in standard form? Are they in slope intercept form, that y equals mx plus b? Are they in some other form that you need to rearrange them into one of these forms? Okay, so the way the systems are set up is going to help you decide which method to use. If we look at graphing, now let's start with graphing from y equals form, that y equals mx plus b, or that slope-intercept form. Let's say we have the two equations, 4/3 x plus 3 and y equals -2/3 x minus 3. These are in slope-intercept form. The y-intercept happen to both be 3 and -3 here. And then the slopes are the number with the x. You've been graphing like this since middle school, I swear. So if you take the first equation, you're going to start at +3 on the y-axis, the y-intercept. 1, 2, 3, put a point. And the slope is 4/3, so from there you're going to go up 4 and over 3. 1, 2, 3, 4, 1, 2, 3, put a point. 1, 2, 3, 4, 1, 2, 3. We're off the page, but we're going to put a point. I'm going to grab a line. I'm going to start here. Whoops. It's going to be something like this. I don't know what that is. Look at that. Okay. Now I'm going to do my other line. I'm going to start at -3 for this one. 1, 2, 3, -3. And the slope is -2/3, so I'm going to go down 2, but still over 3 to the right. So down 2 over 3, down 2 over 3, and what I can do is follow the same pattern, but maybe go up 2 and over 3 this way, and it looks like we're going to be intersecting right there. 3, and so I'm going to grab another line, and I'm going to go like this. And maybe I can even extend this line a little bit more. Oops, not that one. This one. A little bit more so that we can see the intersection point is right here at -3, -1. Because they were in slope-intercept form, I started with the y-intercept, and then I used the slope to move me up and down. -3, -1. This is graphing in slope-intercept form. Not to be confused from the next situation, which is going to be graphing from standard form. Let's write that up here. Graphing from standard form. So what that means is you're going to have two equations, but they're going to be in that ax plus by equals c form. For example, if I have 5x plus 2y is equal to 20, or x plus y is equal to 7. This is where we want to take the little square and cover up. Okay, maybe you can just imagine you have a little square here. If I cover up the x part, then I have 2y is equal to 20, or I know that y is equal to 10. And if I cover up the y part, then I know that 5x is equal to 20, or that x is equal to 4. So if I put those on here, 2, 3, 4 for x, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 for y, grab a line, intersection, or draw the line. If I do the next one, if I cover up the x, I just know that y is equal to 7, and if I cover up the y, I just know that x is also equal to 7, so I have 4, 5, 6, 7, and I have 1, 2, 3, 4, 5, 6, 7, and if I draw a line between those, then it looks like I have a nice intersection point right here at 1, 2, 1, 2, 3, 4, 5, 2, 5. Now if I want to check, I could just plug that in. Is 2 plus 5, 7? Yeah, it works for that one. 5 times 2 is 10, plus 2 times 5 is 10, that's 20, perfect. So I just did a little verbal check there. That intersection point is the solution to both equations. Graphing from standard form, I'm using the x and y intercepts, and then connecting them with a line. Okay. Matrices. When do we want to use matrices? We want to use matrices when the equations are in standard form. Okay, for example, x subtract y is equal to 2, 2x plus 3y is equal to 9. If I set up my first equation, then I'm going to take a 1, that's we know is there, and this would be a negative 1, 2 and 3, x and y is what we're looking to find, that's the unknown, and we have 2 and 9 on the end. And I'm going to plug this in for matrix A, I'm going to plug this in for matrix B, and then I'm going to pull in my calculator, matrix A to the negative 1 power times matrix B, and that's going to be equal to whatever x and y is, my solution. That'll be my solution there. So I think I've actually plugged this into the calculator already. If we go to matrix A, let's just go check that this was 1, negative 1, 2, 3, which is what we want. And I'll go back to matrix B, and that is 2 and 9. So that looks good, so I can go quit. I'm going to pull up matrix A to the negative 1 power times matrix B and hit enter, and I get a solution of 3 and 1. So I'll bring that back to my page, and I have a solution that is 3, 1. That's my solution. Okay, and again, I could check that verbally if I need to. If I plug in 3 for x and 1 for y, well, 3 minus 1 is 2. I have to check the second equation because it has to work for both equations. 2 times 3 is 6, 3 times 1 is 3, 6 and 3 is 9, so that works. Check. If both of your equations are not in standard form, but you really want to use a matrix, then you just are going to have to convert or, alter the equation so that it's in standard form. Maybe you had to bring the y over or the x over, that sort of thing. But if both are in standard form to begin with, then a matrix equation is a nice option. All right, how do we do tables? If we go to the next example, tables work really well when both equations are in slope-intercept form, that y equals mx plus b form. So let's say I have 3x subtract 4 and y equals negative 3x plus 2. Thank you. Let's go to the calculator. You're going to look to see in the calculator when both y values are the same. Okay, so back to the calculator. I can clear that. I'm going to go to my y equals. I'm going to plug in 3x subtract 4, and I'm going to plug in negative 3x plus 2, and I'm going to go to my table. And I'm looking for when the y values are the same. And I think you can see right here, when x is 1, y is negative 1 for both of them. So 1, negative 1 is going to be our solution. So if I go back to this, and I need this, 1, negative 1, negative 1 is the solution. Okay, because it looked like in the table we had x was 1, and y1 was negative 1, and y2 was also negative 1. So that's how we knew it was the solution, because the y values were the same. And we can double check that here, right? If I plug in 1 for x, 3 times 1 is 3, minus 4 is negative 1. I get that for y. Or if I plug it in here, negative 3 times 1 is negative 3 plus 2 is negative 1 for y, so that works. Phew! I hope I'm not talking too fast, but remember these are all methods you've done before. This is just review. Here we are with setting equal. Setting equal is another method you use when they are in slope intercept form. Let's say we have y equals 3x plus 4 and y equals negative x minus 4. Well, setting equal means since they're both equal to y, you can set the equations equal to each other. So I might say something like 3x plus 4 is equal to negative x minus 4 because they're both equal to y, so these two parts must be equal. Well, here I just want to solve this equation then for x, get the x's together. So I might, those of you that like to draw the line down the equal sign to remind yourself to, if you do one thing on one side, you have to do the same thing on the other side. The x's cancel there. I'm left with 4x plus 4 is equal to negative 4. I'm going to subtract 4 here and here, so now I have 4x is equal to negative 8. If I divide by 4 on both sides, then I'm left with x is equal to negative 2. Now, you're not done yet. Don't be confused. You need to find the y value as well. Take one of these equations, it doesn't matter which one. I might take y equals 3x plus 4. I'm going to plug in my x value for the x here. So it's going to become 3 times negative 2 plus 4. Well, that becomes negative 6 plus 4, or y also is equal to negative 2. So my intersection point is negative 2, negative 2. And again, I can plug those in here to double check if I had plugged in negative 2 for this x. The negative of negative 2 should be positive 2 minus 4 is negative 2. Sorry, I don't know why that took me so long. Yes, so that works as well, right? Because positive 2 minus 4 is negative 2. So that worked as well. Okay, linear combinations. This happens to be one of my favorite methods because I love just doing out algebra. And linear combinations is a lot of algebra. Linear combinations is going to work best when you have both equations in standard form. Okay, sometimes you might hear linear combinations called elimination, depending on the high school that students went to or where they learned this. It's also sometimes called elimination. Here's an example. 2x plus y is equal to 5. 3x minus 2y is equal to 4. Remember, the whole part about linear combinations is you're combining the equations, or the reason some people call it elimination is because you're eliminating one of the variables. In order to do that, you need to have the coefficient, the number in front of the variable, be the same value, but one's going to be negative and one's going to be positive. And this is where you need to be sophisticated in your thinking. Is it easiest to eliminate the x right now or the y? I can see right away that it's going to be easiest to eliminate the y if I multiply the top equation by 2. Because I'll end up with a positive 2y here, and I already have a negative 2y in my second equation, so those can be eliminated. So I have to rewrite this. This is going to become 4x plus 2y is equal to 10, because I've distributed this 2 to all 3 parts. My second equation stays the same. 3x minus 2y is equal to 4, and I'm just going to combine the equations, add them. Well, that eliminates those. 4 and 3 is 7x. This becomes 14. Divide by 7. We can very clearly see that x is equal to 2. Just like before, I'm not done. I need to find my y value. So I'm going to take any of these 4 equations. I can take the original one, I can take the one after it's multiplied, or I can take the one that I didn't change. And I'm going to take, I'll just take 2x plus y is equal to 5. And I know that since x is 2, I'm going to plug in 2 for x. And I know that that becomes 4 plus y is equal to 5. And I want to get the y by itself, so I'm going to subtract 4 from both sides. So y is equal to 1. And so I believe my intersection point is 2, 1. I want to just verbally check that. I can go 3 times 2 is 6. 2 times 1 is 2, 6 minus 2 is 4, so that works out perfectly. So standard form for linear combinations. Here's my second favorite method, and this is going to be the one that might be the most useful for us sometimes, because substitution we use when typically, this is, we don't want to say always, but typically when one equation is in standard form and the other equation is in slope-intercept form. And so if you look at this example, 6x minus 7y is equal to 28. Y equals 5x minus 4. Let me just switch colors here so that you can see. Since y is equal to all of this, I can replace it in this equation. By doing that, I only have one variable left, so I can solve for x because I just have x. If I have x and y, I have two variables I can't solve for. So what this looks like is 6x minus 7 times 5x subtract 4. So I plugged this whole part in where y was before, because that's what y is equal to 28. I need to do the distributive property first. I'm just solving for x now. 6x minus 35x plus 28 is equal to 28. Is this going to work out funny? 6x minus 35 looks like that's going to be negative 29x plus 28 is equal to 28 minus 28. Why is this being funny? Negative 29x is equal to 0? Sorry about that. Had to pause for a second. Don't forget, when you divide by 0 by a number, that it's just 0. So we have x is equal to 0. Perfectly fine. When you take that x, plug it in for the x in the y equals equation. Y equals 5x minus 4. So you're going to go y equals 5 times 0 minus 4, because you're plugging in the x value, or y equals negative 4. I don't know why that's still in parentheses. So if I have an intersection point of 0 and negative 4, I can just double check in my top equation. Well, 6 times 0 is just 0. Negative 7 times negative 4 is positive 28. 28, it checks out perfectly. So substitution is a nice method to know when you have one in standard form and one in slope-intercept form. I think we're on to the last one, which is some word problems. These are some very typical situations with word problems involve two parts. One might be just a number of items, and then the second part would be the value of the items. And so let me give you the example. So let's say we have 10 animals in a barn. Very typical Vermont problem, right? And those animals are, these animals are pigs and ducks. Okay? And so we have 10 animals in a barn. These animals are pigs and ducks. There are a total of 36 legs on those pigs and ducks. How many of each animal are there? Well, here's where you're going to create two equations. The first equation is going to be the number of items. Well, if I have a total of 10 animals and I have pigs and ducks, then those are my 10 items that make up, right? The pigs and the ducks make up my 10 items. Now I'm going to put some value on those items, okay? If I have a total of 36 legs, well, how many legs do pigs have? Hopefully you're saying 4. Pigs have 4 legs, and ducks have 2 legs, so this is the value equation. From here, I can choose any method to solve this. What I might do is, since I love linear combinations, I think I'm going to multiply this top equation by negative 2. So negative 2p minus 2d is equal to negative 20, then 4p, I'm just rewriting the bottom one, 2d is equal to 36. I did negative 2 on the top because my ducks eliminate there. I have 2p is equal to 16 divided by 2. P is equal to 8. Once I know P, if it's supposed to be 8 plus D is equal to 10, then I know D is equal to 2. Okay, so I have 8 pigs and 2 ducks as a way to have 36 total legs of pigs and ducks in my barn. Sometimes the value of items is a price of something. If I have t-shirts and pants and a total of 36 of them, and t-shirts cost $10 each and pants cost $40 each, how many can I buy if I have $200 or something like that? Okay, so the number of items and the value of items, those are the two equations that you want to get. That is all I have to share today. What you're going to want to do is there's a bingo practice sheet. There's a word problem sheet to do. And there's a gold summary sheet where you're going to want to put a lot of these examples down so that you can use that gold sheet on your quiz and then eventually on your test. Good luck. Thanks for listening.